Okay, in a video on KL divergence, um, we see uh, this expression of the expected value, which is okay. But here he goes on to another step here, and I wanted to explain that clearly. So that step there is sometimes called the law of the unconscious statistician. Although actually I've never really heard of that before, but that's what sometimes they call it. Really, it's just talking about um, the expected value of a function of a random variable. But anyway, let's talk about it here. So a quick review of what we mean by a random variable and talking about just the discrete case. So suppose a couple plan to have 3 children and are interested in the number of girls they might have. This is an example of a random variable. So if we want to break it down and be really technical, we would say the sample space looks like this. So you could have boy, 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 you could have boy, boy, girl, you could have boy, girl, boy. So this is the sequence of 3 children. And you could have girl, girl, girl at the end. So there are 8 possible configurations. We would consider them all equally likely. From this sample space, we can talk about the number of girls. So here the number of girls is 0. Here the number of girls is 1. Here the number of girls is 1. And here the number of girls is 1. So for these 3 cases, the number of girls, these are the cases where the number of girls is 1. So that's this, and this, and this. And each of these has a probability. Oh, here he says, normally we would say that these are all equally likely, but he's trying to be more careful. So he says the probability of a boy is slightly more likely than the probability of a girl. Here, the probability of a boy is 0.52, so it's not 50%. So if you're like that, if you're saying that, then the BBB is slightly more likely than BBG, for example. So here he writes the probability of BBB, BBG, and so on. So these 3, this one, and this one, have 1 girl, and they all, if you check the probabilities, all have the same. And and those are the 3 cases where you have 1 girl. So the probability of, this is X, the number of girls, so you can have 0 girls, 1 girl, 2 girls, or 3 girls. And the probability of 1 girl comes from these 3 cases, which is 0.3 plus 0.3 plus 0.3. And if you add those up, you get 0.39. Now, if you want the probability of no girls, that's only BBB, and that's 0.14. And so that's 0.14. And you want the probability of 2 girls, then you have to look at the cases where there are 2 girls, which is this one and this one. So, so this is the number of girls, and here's the probability of 0 girls, probability of 1 girl, 2 girls, and 3 girls. Okay, so now we have this random variable here, the number of girls, and the probability distribution. So now we can talk about what's the expected number of girls, or the expected value of X. And we've discussed this before. And well, first they do, what's the probability that X is less than 2, meaning less than 2 girls, meaning no girls or 1 girl. So the probability of no girls is this from that table. Probability of 1 girl is this from that table. So you add them up and you get that. Okay. Okay, so we reviewed the idea of a expected value of a random variable. So now we want to get to that part that was in the video, that the one step that I wanted to clarify. So that is where we're talking about a function of a random variable, and then we want to know what's the expected value of a function of a random variable. So first they say functions in general. So they say go back to the, this is several pages later, but they say go back again to the planning of a family of 3 children. So we just finished talking about that. Now they say that suppose that the annual cost of clothing, so R, is going to be the cost of clothing, the annual cost of clothing, is a function of the number of girls. So that sounds like a kind of a strange relationship, that there's a cost of clothing is dependent on the number of girls, but maybe what they mean is, well, let's not worry about what they mean, but just suppose that it is a function of the number of girls, and suppose that this particular function is this one here. So what do they mean? So if you have 0 girls, we can say what's the cost? It's $500 because these are 0 terms. If you have 1, then it's minus 100 plus 300, so it's plus 200. And if you have 2, then you calculate that. And if you have 3, then you calculate that. So now we have that the cost of clothing is some function of the number of girls in the family. So let's think about it. If there's 0 girls, then we just figured out that the cost was 500. We didn't do this one, but they did it for us. It was 700 for 1 girl, 700 for 2 girls, and 500 for 3 girls. So I guess the cost of clothing goes up if you have boys and girls. You can see this is boys and girls, both of these. So I guess the idea is like you're going to give the clothes, once one child grows to a larger size, then you give their clothes to the younger child, at least some of the time. So if you have all girls, you can just keep passing down the clothes, but if you have boys and girls, then it's going to cost more. So maybe that's what they're talking about. That's what they say here. And there we saw in that calculation here, we saw that actually there are only 2 different values for R. It can either be 500 or 700. So they sort of simplify this table. They say it can either be 500 or 700. And what are the ways that it can be 500? Well, we saw that over here. It was 0 girls or 3 girls. So 0 and 3 contribute to the 500, and 1 and 2 are the ones that give you 700. And then we can also ask, well, what's the probability that it's 500? So that there are 2 ways that it can be 500, 0 or 3 girls. So that's 0.14 plus 0.11, which is 0.25. And then we can also do the same kind of calculation for what's the probability that there's that it costs 700, and that comes from 1 and 2 here. So that's if you combine their probabilities, this one and this one, you get 0.75. So what's the probability that it's 500 girls? 0.25 and $500. 0.25 and $700, 0.75. Okay, so now that so this is a new random variable, and we might ask, what's the mean of this random variable? In other words, what's the expected value of this random variable? And we do the calculation the same way we do for any expected value of a random variable, of any random variable. We take the value of the random variable times its probability, and the value plus the value, the other value of the random variable times its probability. And that if you do this times this, I guess you get this. If you do this times this, I guess you get that. So you sum them up, and this is the expected value for the cost of clothes. Okay, so that's straightforward, but what we want to show is that we can do this calculation in a slightly different way. So what are we talking about? This is what we, no. Yeah, so they say that there's an easier calculation of the average cost. This is the expected value of R, or you can write it as E of R, or you can write it as mu sub R. It means the same thing, just different notation. And they say we can get this directly from table 4-4. Which is table 4-4? So this is table 4-5, and this is table 4-4. Now we didn't do it that way. We just used table 4-5, and we took this times this and this times this, and we added them up and we got this. So that's one way to do it. But what they're going to tell us is that we could have just gone from here, and we could have multiplied this times this, plus this times this, plus this times this, plus this times this. So that's, you might get confused and say, well, isn't that what we just did? No, it's not what we just did. we did this times this and this. We only did 2 multiplications, but here we're not doing 2 multiplications, so it's not the same. It's different. So, but we could do it this way. So we wouldn't have to calculate, we wouldn't have to combine the probabilities and get P of R here. We could just use the same probability. This is different, right? This is not the same probability function that this is, because this is has 4 possible values. It can't be the same as this one, which has 2 possible values. It's not the same, and we had to go do some extra work to calculate P of R, but we didn't have to do it, is what they're trying to say. And that is, we could just keep the original, or only work with the original probability function, and we still have to go through the trouble of calculating R, which is g of x, but we don't have to go through the additional trouble of calculating P of R. So we can just do this times this, this times this, this times this, and this times this, and we'll get the same thing. So what they're saying is we can just do g of x is R, in other words, this part here. We have to do that, but we don't have to calculate P of R. We can keep the P of x. So again, here we calculated g of x, which is R. We did that work, and we did this work. So we used P of R, but they're saying you don't have to do that. You still have to do g of x, but you don't have to do P of R. You can just leave it with P of x. So that is the idea that was that he showed in this step here. So if you have a function like he was using we didn't use h, he used g. So he wanted the expected value of g of x, which was, g was the number of girls. I'm sorry, g was the amount of, g was the cost of the clothing. You can just do this. So you do have to calculate g, or he's calling it h here, but you don't have to calculate p of, what would it be, like P of h, I guess, or something like that. You don't have to do that. You can just use the regular probability, the original probability function here. So that explains the step going from here to here. Okay, here's one more example. Let's just take a look at this one just for a little more experience in this. So wear and tear on the railroad. So the wear on the axle of a railroad car increases as the load on it increases. Okay, that makes sense. The more weight you have in the railroad car, the more wear and tear, or wear, on the axle. Roughly speaking, though, a doubling of the load x, so if you double the amount of weight in the railroad car, the wear, R, he's going to call the wear, R, will follow the square of x. So if you double the x, the wear, it quadruples the wear. So it follows the square of x. Okay, so suppose that that's true. Now suppose the car passes over an irregular section of track so that the weight on each axle fluctuates wildly according to the distribution. So sometimes the load is 8. Sometimes, I don't know what they're talking about, but sometimes the load is 8, sometimes the load is 20, and sometimes the load is 80. And 25% of the time the load is 8, and 70% of the time it's 70, and 5% of the time it's 80. Calculate the average load, calculate the average wear. So remember that the wear, R, is a function of x. X is a random variable, and the wear is a function of that random variable. Okay, so Okay, so let's see what they do. So first of all, we can calculate the average value of x, which is the average, what is x again? The average load. So that is, you do the calculations as we know, you do this times this, and then add them. You get this, 20. Okay, now the average wear, now we're going to use that formula that we just realized, so we don't have to calculate independently the probability distribution of R. We can just leave the original probability distribution here in the calculation. So we have g of x is x squared, so that's 8 squared, 20 squared, and 80 squared. And then we use the original probabilities and multiply, and I guess so that means we take this times this, we take this times this times this, and this times this, and we get these three numbers. We add them up, and this is the average wear, or the expected wear. Okay, we'll leave it at that, and we'll stop here.